after going through this module, you should be able to firstly understand electronic transitions of diatomic molecules and then use the Franck-Condon principle to predict the shape of the absorption curves. Electronic transitions involve transitions between two electronic states. The energies involved in the transitions are very high, and UV and visible range photons are involved in the transitions. Each electronic transition is accompanied by vibrational transitions, which is the core structure, and each vibrational transition by rotational transitions, which is the fine structure. Now, why is it so? Because we have already seen that the vibrational transitions require much less energy as compared to electronic transitions. So, they will be accompanied by all electronic transitions, and each vibrational transition can also be accompanied by rotational transitions which require lesser energy, and so that will constitute the fine structure. The magnitudes of the involved transitions show large variation. For example, for the electronic transitions, the energies are about 1000 times that of the energies involved in vibrations, and which are about 10 raised power of 6 or million times those of rotation, and hence the three kinds of energies are independent of each other. This is essentially the Born-Oppenheimer approximation, which allows us to write the total energy as a sum of the individual energies. That is, we can ignore any interactions between them. Thus, we may write E, the total energy, is equal to the electronic energy plus the vibrational energy plus the rotational energy. First, discuss the vibrational core structure. We will ignore the rotational energies because they are much smaller than electronic energies, and write for the wave number of the absorbed or emitted photon. Its wave number is given by the change in the electronic energy plus change in the vibrational energy, that is delta T electronic plus delta G V, where delta T electronic is the difference of electronic energies of the first two states and of the involved two states expressed as wave number. Substituting for the vibrational terms for the ground state and excited states, we obtain that the energy of the photon, or rather its wave number, is given by the change in the electronic energy plus the change in the vibrational energy, that is delta T electronic plus delta G as a function of V, which is equal to T electronic prime. Remember that the single prime refers to the excited state, minus T electronic double prime for the ground state, plus omega E prime into V prime plus half, minus chi E prime omega E prime into V prime plus half whole square, minus the whole thing omega E double prime, the whole thing for the ground state. That means omega E double prime into V double prime plus half, minus chi E double prime omega E double prime into V double prime plus half. And in figure we have shown the various quantities involved. Both electronic states are represented as Morse potential energy curves. In the more general case, the excited electronic state has weaker bonding, and so its equilibrium internuclear distance Re prime, again this stands for the excited state, is greater than Re double prime, whereas usual we have represented the ground state by a double prime and the excited state by a single prime. Now, why is it so? Because usually a transition is from a bonding level to an anti-bonding level. So, the bonding is weakened in the excited state and its bond length is increased. The potential well of the excited state is also quite shallow because it is easier to dissociate it, because it is weaker in the bonding is weaker, and so it is easier to dissociate the bond. By convention, spectroscopists label the ground state as capital X and the excited states of the same multiplicity as A, B, C in order of increasing energy. So, the first excited state would be A, the next one would be B, and so on. Here we have shown just one excited state which we have labeled as A, and X is a ground state which is shown in blue, and the red Morse potential energy curve is for the excited state, and you can see that the meaning of all these terms is very nicely shown in this figure, and which shows the electronic transitions. There is essentially no selection rule for vibrational transitions between two electronic states. They are labeled as V prime comma V double prime within brackets, That is, you write down the excited state vibrational quantum number first and then the ground state vibrational quantum number. So, the transition labeled nu bar 00 is from a ground state 0 to the 0 excited state vibrational energy level, that is that the ground vibrational states of the two electronic energy levels. Other absorption transitions are 10, 20, etc., and obviously the energy is increasing because the excited state vibrational quantum number is excited. The 00 transition is also called an adiabatic transition because it is the lowest energy vibronic. This is a new term coming from vibration plus electronic. It is called vibronic transition because it is a combined vibration plus electronic transition between two electronic states. The V prime comma 0 transitions shown in figure also called V double prime is equal to 0 progressions because they have a constant value of V double prime is equal to 0. They all originate from the same V double prime is equal to 0 level. We confine our discussion to this progression since we are studying absorption spectroscopy, and at room temperature practically all the molecules occupy the V double prime is equal to 0 level. Hence, transitions from this level are the most important transitions. You can see these are the transitions and how their energies are changing, and 00 is the lowest energy transition, then you have the 10, 20, and these are shown by the arrows in this figure. So, this is the V double prime 0 progression. This figure shows that a large number of vibrational transitions are possible and electronic transitions are expected to be broad. In equation there are 5 unknowns. Identification of 5 consecutive lines in the spectrum can easily help determine all these unknowns. So, you had 5 unknowns, for example, the vibrational level of the ground state, the excited state, the transition energy, the electronic energy of the ground state, of the excited state, and so on, and all these can be determined because there are 5 unknowns, you need 5 equations. The interaction between electronic and nuclear vibrational motions is known as vibronic coupling. The word vibronic originates from a combination of the two words vibrational and electronic, and is an instance of the breakdown of the Born-Oppenheimer approximation, because up till now we said that they are independent of each other. The shape of the absorption curve is governed by a principle called the Franckcondon principle. So, now we will talk about this principle. In figure we had considered the case where the excited electronic state had a slightly larger internuclear distance than the ground state. We said that the bonding had weakened, so the internuclear distance had become larger. This is not always the case. The excited state may have nearly the same or much larger bond length compared to the ground state. Different shapes of the absorption curve are found in each case. To understand this, let us return to figure. We know that in the ground vibrational state, the molecule is more likely to be found in the middle of the potential well, but as the vibrational quantum number is increased, the tendency shifts to the extrema. You can see in this figure the probability distribution for a diatomic molecule. In the ground state, V is equal to 0 level, the probability is maximum at the center, and as we keep on increasing, the probability starts moving to the extremes and the probability in the center keeps on decreasing, and this is a consequence of the solution of the Schrodinger equation for the anharmonic oscillator. In figure, for the 0-0 transition to occur between the most probable positions of the two states, the molecule would have to constantly increase its internuclear separation during the transition. It would have to make a slanted kind of transition. That is, the blue arrow would be slanted instead of vertical. In short, the Franckcondon principle says that electronic transitions are vertical, and electronic transition occurs so fast, somewhere in the space of 10 raised to the power of minus 15 seconds, so that the nuclei, which are much heavier, do not have time to adjust their positions while the electronic transition is taking place. We will illustrate this with we consider a case for which Re double prime and Re prime are both of the same magnitude, that is, there is no appreciable change in the bonding in the excited state. The vertical transition leads to the ground vibrational level of the excited electronic state, that is, the 0-0 transition is the most intense. A few higher transitions may be observed with low intensity, and these are shown at the foot of the figure. Then we consider another case where Re prime is greater than Re double prime, the more general case, that is the bonding is weaker in the excited state. The vertical arrow now ends at a higher vibrational level, and the level at which the arrow ends is the most intense transition. This is the most general case and gives rise to the familiar shape of an absorption curve. Note that in this case the maximum probability lies at the extrema. Finally, we consider the case Re double prime is much greater than Re prime, that is the excited state has much weaker bonding. The vertical transition takes the molecule to a very high vibrational energy level of the excited electronic state, which is now close to the dissociation limit of the excited state molecule. Figure shows that a few transitions we observe followed by a continuum when the molecule dissociates because it has reached a high enough energy that the bond breaks between the two atoms. Electronic transitions therefore allow us to calculate the dissociation energy from the point of onset of the continuum. We had ignored rotational fine structure, but let us see what that has to do with the transition. If we also include changes in the rotational energy in the spectroscopic transitions, the equation for the wave number of the electronic vibrational transition gets modified to wave number of the photon is given by the wave number for the V prime V double prime transition plus delta E, which is B j into j plus 1, where the nu bar V prime V double prime represents the wave number of the electronic vibrational or the vibronic transition. If both the ground and excited electronic levels possess neither spin nor orbital angular momenta, that is both the lower and upper electronic states are 1 sigma states, that is they are singlets, and they are sigma, that is they do not have any angular momentum. The absorbed or emitted photon can only change the rotational quantum number by 1 unit, and delta J is equal to plus or minus 1 as we have seen for pure rotational spectroscopy. Only this is valid only for 1 sigma to 1 sigma transitions. For all the other transitions, delta J is equal to 0 is also allowed. So, we have the combined selection rule, delta J is equal to 0 plus minus 1, but even in this case J is equal to 0 to J is equal to 0 transition is not allowed, and this is because of the requirement of conservation of angular momentum as we discussed in atomic spectroscopy. Thus, for transitions between 1 sigma states, a PR contour will appear, but Q branches will also appear in other cases. Therefore, the spectroscopic wave number of the photon is given by the wave number of the V prime V double prime transition, the vibronic transition, plus B bar J prime into J prime plus 1 minus B double prime J double prime into J double prime plus 1, and where the two rotational constants with prime and double prime refer to the excited and ground electronic states now. Earlier when we used this notation, we were talking about the ground and excited vibrational levels. Now we are talking about excited states, and the wave numbers for the P and R branches will be as follows. For the P branch, you know delta J is equal to minus 1. So, J double prime is equal to J prime plus 1, and when you substitute that, you find that the nu bar, the wave number for the P transition is equal to the wave number for the V prime V double prime vibronic level minus B prime plus B double prime into J prime plus 1 plus B prime minus B double prime into J double prime plus 1 square, and here J prime is equal to 0, 1, 2, and similarly for the R branch where delta J is equal to plus 1, you have J prime is equal to J double prime plus 1, and here the wave number of the R branch is given by the wave number of the V prime V double prime transition minus B prime plus B double prime into J double prime plus 1 plus B prime minus B double prime into J double prime plus 1 square, and here J double prime can take on values 0, 1 and 2 and so on. These two equations can be combined into another equation which gives you for both the branches the wave number for the P and R branches is given by the wave number for the V prime V double prime vibronic transition minus B double prime plus B prime into M plus B prime minus B double prime into M square, where M can have values plus minus 1 plus minus 2 with positive M values for the R branch, for which delta J is equal to +1 and negative values for the P branch for which delta J is equal to -1. Note that M cannot be 0 as this would correspond to J prime is equal to -1 for the P branch, because here delta J is equal to -1. So, a 0 to -1 transition is not possible because -1 quantum state is not possible. So, that no line from the P and R branches appears at the band origin. There is a band origin, add new bar B prime B double prime. Though these equations resemble those for rotational vibrational bands in infrared spectroscopy, the difference in the rotational constants of the two states are much larger. That is, B prime is much smaller than B double prime here, and bunching of lines on the R branch and spreading out of the B branch is much more noticeable and marked here. The third term in equation quickly overtakes the second term in the R branch, and the band heads appear when the R branch appears to return. After a certain value, it appears as if it has returned, because the positive and the negative terms, they first cancel and then one term overtakes the other. And this is how the rotational fine structure of a vibrational electronic transition looks like. For the Q branch, delta J is equal to 0, J prime is equal to J double prime, and this is not equal to 0, since J is equal to 0 to J is equal to 0 is not allowed transition, and new the V prime B double prime vibronic transition minus B prime plus B double prime into J double prime plus B prime minus B double prime into J double prime square. The Q branch lies on the low wave number side of the origin, since both the last two terms are negative. So, we will summarize what we have learnt in this module. Electronic transitions involve much larger energies than vibrational and electronic transitions. Each electronic transition is accompanied by vibrational and rotational transitions. The combination of vibrational transitions with electronic transitions is called vibronic transitions. There is no selection rule for vibrational transitions between two electronic states. The Franck-Condon principle governs the intensity distribution of vibronic transitions, and the R branches in the rotational electronic spectra show band heads.